Have you ever stopped to actually think about why ice is so slippery? I mean, it seems like one of the simplest questions in the world, right? It's something we've all felt, whether you're carefully stepping on a frozen puddle or watching a skater just glide effortlessly. Well, today we're going to dive deep into the really surprising science behind this everyday mystery.
So let's get right to it. It seems obvious. Ice is slippery. Well, because it's ice. But the real reason, down at the molecular level, has actually been a scientific puzzle for more than 150 years. And let me tell you, the answer is way more fascinating than you probably think.
For a long time, science really had two main explanations. And if you ever took a high school physics class, you probably heard one or both of these. Let's call them the usual suspects in this slippery ice investigation.
Okay, so first up is pressure melting. The whole idea here is that the super concentrated pressure under a tiny skate blade is enough to literally force the ice to melt, which creates this nice little lubricating layer of water. Makes sense. Then there's frictional heating. This one says that the friction from, say, a ski sliding across the snow generates just enough heat to melt the very top surface of the ice, and again, you get that slippery water layer. Both of these sound totally plausible, right?
Well, here's the thing. When scientists actually run the numbers and do the experiments, these theories start to fall apart. You'd need a frankly ridiculous amount of pressure to explain how you can still ski when it's minus 20 Celsius out. And some really high-tech experiments have tried and totally failed to find enough heat from friction to explain just how slippery things get. So if it's not just pressure and it's not just heat, what on earth is it?
To get to the real answer, scientists had to go way beyond what we can see, even beyond what normal lab equipment can measure. They needed a way to peek inside that hidden, moving, chaotic interface between the slider and the ice, atom by atom.
And this is the tool that changed the game: molecular dynamics simulation. Just think of it like the ultimate virtual microscope. It lets researchers build a perfect block of ice inside a supercomputer, and then they can simulate exactly what happens when you slide something across it, tracking every single water molecule as it moves.
And this right here shows you exactly what those simulations found. See the bottom? That's the perfect, neat, hexagonal structure of solid ice, the crystal. But now, look at that layer just on top of it. It's a complete jumble, a chaotic mess of molecules. The physical act of sliding has literally sheared the top of that crystal apart, creating a disordered liquid-like layer. And the key thing here is, this isn't melting from heat, it's a mechanical transformation.
So this leads us to the real core finding, which is a total paradigm shift in how we think about ice. It's not about heat, it's all about mechanics. Okay, the scientific term is displacement-driven amorphization. I know, it's a mouthful, but let's just break it down. Amorphization just means the ice loses its neat crystal structure. Displacement-driven means it's caused by the physical movement of sliding. So, putting it together, the sliding itself is mechanically smashing the ice into a disordered, liquid-like layer that acts like a lubricant. This right here is the real reason ice is slippery. Not heat, but pure physical force.
And this is just a brilliant way to picture it. Imagine spreading butter straight out of the fridge. That first pass is really tough, right? But with each scrape of the knife, you're mechanically working the surface, creating this softer, smeared layer that makes it easier to glide, even though the butter itself hasn't actually warmed up. That's exactly what's happening on the surface of ice, molecule by molecule.
And they've got the math to prove it. The simulations show that the thickness of this messy layer grows with the square root of the sliding distance. This is the smoking gun, people. It proves that the amount of this liquefaction depends on how far you've slid, not on temperature. It's a direct result of the mechanical movement.
And this is where the evidence gets really weird and counterintuitive. The simulation showed that incredibly cold ice, and I'm talking crazy cold, like minus 263 degrees Celsius, it actually forms this disordered layer faster than warmer ice. Just think about that for a second. If this was all about friction and heat, that would be completely impossible. It's some of the most powerful proof we have that we're dealing with a fundamentally mechanical process.
But, of course, that raises a brand new question. If colder ice makes this lubricating layer faster, then why does it feel so sticky and slow when you're trying to ski on a really cold day? Well, the story, it turns out, has a couple more crucial factors that decide what that slipperiness actually feels like in the real world.
So yeah, let's tackle that paradox head-on. Why does our own experience seem to completely contradict what the simulation is telling us? The answer isn't about whether the layer's there or not, it's all about the properties of that layer. So that amorphous layer that forms on really cold ice is incredibly viscous. Think of it like trying to slide on top of thick molasses. Sure, the layer is there, but trying to move through it creates a ton of drag. Now, on warmer days, when you're closer to 0 degrees, that layer is much less viscous. It's more like runny syrup. It's still a lubricant, but it's a much more effective one. So the reason it's hard to ski on cold days isn't because you're not making that liquid-like layer. It's because the layer you're making is just super thick and sticky.
Okay, so we've got our mechanical process creating the layer, and we've got viscosity telling us how that layer feels. But there is one final critical piece to this puzzle, and it has nothing to do with the ice. It's all about the object that's doing the sliding.
What you're seeing here are two different surfaces sliding on ice in the simulation, and the key is how they interact with that amorphous water layer. On the left, you've got a hydrophilic, or water-attracting surface. See how the water molecules kind of bunch up and cling to it? That creates drag. But now look at the right. That's a hydrophobic, or water-repelling surface. The water layer just glides right past it. The surface doesn't stick to the water, and you get a much smoother slide.
And the effect this has is absolutely staggering. The simulations found that using a hydrophobic surface can cut the kinetic friction by a full 50%. 50! That's because the water-repelling surface lets that lubricating layer do its job with almost no resistance, which dramatically cuts down on both drag and adhesion.
So, what does this all add up to? Well, it means we pretty much need to rewrite the entire story we tell ourselves about ice. It's not a simple little story about heat and melting anymore. It's a much more complex, much more dynamic story about mechanics, forces, and molecular chaos.
So, let's just quickly recap the main takeaways. Ice's slipperiness is not really about melting. It's caused by the mechanical smashing of the ice surface into a messy, liquid-like layer. Now, this can happen even faster on super cold ice, but that layer is also much stickier because it's so viscous. And to get that perfect, effortless glide, you need two things. You need that lubricating layer, and you need a smooth, water-repelling surface, just like a polished steel skate blade to slide on.
And this leaves us with a really fascinating final thought. This whole process, this displacement-driven amorphization, it's not just something that happens to ice. You know, similar atom-by-atom wear and tear happens in super hard materials like diamond and silicon. It suggests that on the tiniest scales, friction and wear aren't just about stuff rubbing off. It's about a fundamental mechanical reordering of matter itself, which just makes you wonder, what other secrets are hiding at the surfaces all around us?